Hello, Astronomy. Mr. Janowski here. This is part 10 of the chapters 14 and 15 slides. So, in the last part, we talked about the very weird things that happen if you fall into a black hole, or if something falls into a black hole, and how it is very different from the perspective of the thing doing the falling into the black hole and from the perspective of someone outside of the black hole watching that happen. So, very weird stuff. So, let's continue talking about some of the weirdness of black holes. So, the big question from the last part of the slides, do events inside of black holes happen? And the answer is, yeah, I don't know. Nobody knows. It's weird. We have different theories. It just gets really weird. Bizarre metaphysical implications to all this stuff. Do events that happen actually happen? Very weird. So here is a very good Kurzgesagt video about black holes. So this is actually part one of two. I didn't like part two as much, but yeah, it covers a lot of the things we've been talking about: how black holes are formed, the weirdness of falling into the black hole, how you seem to speed up if you're watching something fall into a black hole, how it will seem to speed up for a while and then slow down and then kind of pause and then get red and dim and fade away, and just yeah, lots of the weirdness. So, quickly, I wish we were there in person for me to go over this because this is just a really weird thing. The idea of space-like and time-like dimensions. So, in general relativity, well, let me rewind a little bit. So, we like to think before Einstein that we live in a three-dimensional world. So, up, down, left, right, forward, and back, and then there's this separate thing called time. So, according to Einstein and general relativity, that's not the way it works. Time and space are very much connected, and we live in what's called four-dimensional space-time. Now, if you're outside of a black hole, such as we are now, think of the three spatial dimensions. So you could hold your thumb in front of you, you could move it up and down, you can move it left and right, and you can move it forward and back. So that means in each of those dimensions, you are free to go in either direction. Time is different, however. You can only go forward in time. You can't, if you just sit there and wait, you're going to go forward in time. You have no ability at all to go backwards in time to, 3 seconds ago, 10 seconds ago. You just can't do that. But no matter what you do, you are going to go forward in time. So here we are outside of the black hole, and we have space-like dimensions in which you are free to go in either direction, and you also have a time-like dimension in which you are always going to go in one dimension. So one of the very weird things about black holes and our models of them and the math about them says that if you cross the event horizon of a black hole, the one of the spatial dimensions, the dimension that is towards the singularity at the center, stops being space-like, meaning you can no longer go forwards and backwards along that dimension towards the center of the singularity. That one becomes time-like. You can only go forward, and just the possibility of going backwards away from the singularity, once you've crossed the event horizon, it just doesn't exist. You don't have that possibility. And even more bizarre than that, perhaps, is the fact that time seems to become time inside the event horizon of a black hole, stops being time-like and starts becoming space-like. So you can go forwards and backwards in time inside of the black hole. However, you can only go forwards towards the center of the black hole because time is now space-like, and one of your spatial dimensions becomes time-like. So yeah, just really bizarre stuff, difficult to wrap your head around. I don't understand it, but I don't know. We're going with that. I don't know. So moving on. So seeing a black hole. Yeah, it's going to be kind of difficult because light can't escape from the event horizon of a black hole. So how can you see something if, by definition, no light can come from that thing? So yeah, weird things about black holes. Just quickly, when the star, this very massive star, 20 solar masses, collapses and leaves a core of 3 times the mass of the sun, and that core is going to collapse because not even neutron degeneracy pressure can support it against gravity anymore, a black hole will form, and the black hole is going to form from the inside out, which seems weird. Yeah. And it just gets bigger and bigger as more mass falls onto it. So there's your formula for the Schwarzschild radius. And you can see that as m gets bigger, m is the only variable in that on the right side of that. As m gets bigger, the Schwarzschild radius is also going to get bigger. So yeah, if you're inside the black hole, if from within, from the event horizon and within, no light can escape. But anything that's even just a little bit outside that black hole, it's outside the event horizon, so that light can escape. So for some bizarre reason, as things start falling into the black hole, you get what's called an accretion disk, and you often get these jets. So if you look at step 3 of this picture up here, you've got a black hole, you've got material going around it. You've got these weird jets. So yeah, again, black holes, they by definition don't emit any light, so they're going to be difficult to see. Well, essentially, they're going to be impossible to see directly. But you can see them indirectly. So one way for this to happen is if that black hole has a binary companion. And if you remember from a few chapters ago when we did binary stars, stars the size of the sun, it's about 50-50 if they're going to have a binary companion. But the more massive stars, actually most of them do have binary companions. So let's say you have two stars, they're both being binaries. One of them, reaches the end of its life, collapses, and it was supermassive, so it ends up being a black hole. Well, the binary's still there. So instead of having two stars in orbit around each other, now you have one star and one black hole. So the immense gravity of this black hole might start peeling stuff away from its companion, and that material is going to swirl around and swirl around. And so if we're looking at this part of the picture here, right here in the middle, you have the black hole, and this material around it is called the accretion disk. So accreting means to add to. So yeah, you've got this stuff outside of there. So gravity's pulling this stuff in. It's going to start moving faster and faster and getting hotter and hotter. And eventually, this material in the accretion disk can start to emit X-rays if you get it hot enough. So this is still outside of the event horizon, so you can see this stuff. So if you're getting X-rays from the accretion disk, well, you're not getting any light by definition from the black hole itself. But if you're getting X-rays off of this, that's a pretty good, hint and clue that there is a black hole there. And yeah, the other thing is if these are, eclipsing binaries in a sense, although instead of two stars eclipsing each other, you've got a black hole and a star eclipsing. You might get, the X-rays sometimes getting all the way through, sometimes being blocked by the companion star, and then sometimes getting through again. So Cygnus X1. So this is not an eclipsing binary. However, this is the first thing that we saw that pretty much everyone agreed, yeah, this has to be a black hole. So we saw a blue supergiant in orbit around some kind of X-ray source, and it wasn't clear what the X-ray source was, but they're binaries, and if you have binaries, you can figure out the masses of the things. And it turns out this X-ray source had to have a mass of about 15 times the mass of the sun, which is far too massive for this to be a neutron star. So even though you weren't seeing the thing itself directly, you were seeing X-rays, and the idea is that, well, the X-rays must have been coming from the accretion disk around this invisible black hole. So by figuring out the mass of the whole thing, it was just kind of conclusive evidence that, yeah, there's got to be a black hole there. So All Things Must Pass, Hawking Radiation. So All Things Must Pass is the title of a George Harrison solo album, and it's a wonderfully poetic idea. The idea that nothing lasts forever, that's the natural order of things. Things come, doesn't matter how wonderful they are, they're going to go away eventually. And you just have to accept that. So I don't know why I'm getting so philosophical. This is supposed to be astronomy here. So anyhow, Stephen Hawking came up with this idea of Hawking radiation. So we sometimes like to think of black holes as just being kind of one-way streets. They're just big drains that just pull things in. And because the escape velocity is the speed of light, well, doesn't that mean that nothing can ever get away from them? And, early black hole thinking kind of went that way. But Stephen Hawking came along and figured this out in the 70s, that by some complicated process involving quantum mechanics and the Heisenberg uncertainty principle and virtual particles, Yeah, it's bizarre quantum mechanical stuff. Black holes must eventually emit, not eventually, actually kind of continuously emit uh, a little bit of radiation, and we call this Hawking radiation. So this is something we have never directly detected. It is predicted to be very, very, very faint. So basically, damn near impossible to actually detect, at least by what we have now and the way we're thinking now. But theory suggests that this should exist. And if we had ever observed this during Stephen Hawking's lifetime, he certainly would have won a Nobel Prize for it. You can't win a Nobel Prize posthumously. So Stephen Hawking passed away in 2018, as the picture says. And so, yeah, he never actually won a Nobel Prize, and he never will, because we only give them to living scientists, is one of the rules of the Nobel Prizes. So this is basically Hawking's greatest idea, and totally Nobel worthy, only we could never actually detect it. So if anyone had detected it, yeah, they would have rushed and gotten Stephen Hawking his Nobel Prize, but didn't happen. So yeah, back to what this Hawking radiation actually is. So yeah, this is very weird quantum mechanical stuff. So basically, by the Heisenberg uncertainty principle, even empty space is not really empty. You can't say with absolute certainty that there's no energy in a certain area. So what that means is over very short amounts of time, you're kind of allowed to borrow energy out of nothing and form two particles. And as long as these particles come into existence and quickly recollide and then disappear, you haven't violated the law of conservation of energy. And it's the Heisenberg uncertainty principle and just weird quantum mechanics stuff that allows that. So the basic idea of this is that if that happens, if just outside of the event horizon of a black hole, for these weird quantum mechanical reasons, two virtual particles come into existence, and these guys would normally almost instantly recombine and then just disappear from the universe, so everything's cool. But if one of them happens to fall into the black hole and the other one happens to get away, well, they're never going to be able to recombine. So this is a mechanism by which a black hole could eventually lose mass, and mass is energy, and it would just slowly radiate away its energy. So, yeah, according to this is the all things must pass idea, is black holes will eventually evaporate. And basically, a black hole that's existing, we believe, is constantly going through this process. It's constantly shedding mass through this weird quantum mechanical thing, Hawking radiation. But as long as there's some material that can fall in, the amount of material that's being added just by falling in is going to be much greater than the amount that's going to be evaporated. So, yeah, this evaporation process takes a very long time. So, for a small black hole, 3 times the mass of the sun, this is the smallest black hole that you can have from the collapse of a star, it would take about 10 to the 68 years for one of these black holes to happen, which is an absurd amount of time. So, this is 10 to the 68 years written out right here. And if you compare that to this number, 13.8 billion years, that's the current age of the universe. So there has not been nearly enough time for any one of these black holes to evaporate this way. So yeah, this stuff is all theoretical, hypothetical, but the theories we have suggest that this should be going on. So here's a couple of videos I'll link to talking about Hawking radiation in more detail. So yeah, good ones. It's a shame Stephen Hawking's not with us anymore. But on the bright side, despite he had Lou Gehrig's disease, ALS, and he was not expected to live past his 30s, I believe is what it was. Yeah, he did. He lived much longer than anyone expected, and he got a lot out of his life. He got a lot done, and yeah. So yeah, sad that he's gone, but on the bright side, he did accomplish a lot. So here are a couple of cahoots. Well, here's one cahoot. Here's another cahoot. If you feel like playing, just to review the stuff from this chapter. So ordinarily, this would be the last part of the slides, and then we would have the test, and then there would be one more thing about the EHT, the Event Horizon Telescope image they got last year. But Yeah, so basically this is essentially the end of the slides. I will make one more video about the EHT observation, but this is basically the end of the slides. So yeah, quick review. If no light escapes from a black hole, how can we see one? See being in scare quotes. Well, you can't directly see the black hole itself, but if that black hole is pulling in matter, if there's a binary, so here's the binary companion, here's your black hole in the middle. If this is pulling in matter, well, that matter is going to get superheated. It's going to start emitting X-rays, and while the X-rays are coming from something that is outside the black hole, which the accretion disk is, you can see those X-rays. So yeah, you can't see the black hole itself directly, but you can see the X-rays. And what is it that causes black holes to evaporate? That is Hawking radiation. Yeah, this kind of bizarre quantum thing. So yeah, I'll just read it here. Quantum fluctuation produces pair of photons. Normally they recombine an instant later, but if one of the pair enters the black hole, the other may travel away, subtracting energy from the black hole. So yeah, bizarre stuff. So hopefully you found this interesting.